Hey guys, this is my first ever physics video. Today I'm going to talk about the photoelectric effect, which was the complete breakthrough for quantum mechanics. It was so important, in fact, that Einstein got a Nobel Prize for this discovery, while he didn't get a Nobel Prize for his famous E equals to mc squared. So what is the photoelectric effect? Well, from our prior knowledge of waves, we can know that light is a transverse electromagnetic wave that can travel through vacuum, but there's a slight wrinkle in that information. So the photoelectric effect was the observation of emission of electrons when light was shined upon some metals. In other words, scientists observed that when they shined light upon some metals, they emitted electrons, here onwards referred to as photoelectrons. Now, the wave theory for light predicts certain things for these emissions. The first prediction was time lapse. Wave theory predicted that there should be a certain time lapse between the incident of the light wave and the emission of the electrons, or the photoelectrons, to be more precise. So this can be intuitive. So if light is traveling like a wave, then energy would be gradually supplied to the metal, and therefore it would take some time for the photoelectrons to absorb the energy as it comes, and then they get emitted. So because light is traveling like a wave, is like a continuous form of energy. It is a continuous supply of energy, so it'll take like some time before the electrons absorb enough energy and then get emitted as photoelectrons. The second prediction was that if you think of light wave as like an intense laser beam, the more intense it gets, the more energetic the electrons will be. So if this laser beam here was very intense, then obviously the photoelectrons will be more energetic, they'll have a higher velocity. And the final prediction was that the frequency had no effect on the photoelectron emissions. However, it turned out that the actual observations contradicted each of these three predictions. There was insignificant time lapse. The intensity of the incident light affected the number of electrons that came bouncing off. So the light actually acted as a hammer. The more intensely you strike, more electrons come bouncing off. And the frequency was the key. The higher the frequency, more energy was provided to the electrons, and they came out with a higher kinetic energy. So Einstein formulated this theory that light may actually be in the form of packets, particles, photons, where each photon has the energy of E equals to hf, where h is the Planck's constant and f is the frequency. So this is the total energy supplied when when the photons hit the metal surface, as quantized by the Einstein theory. So, well, the question for quantum mechanics was, does light behave as a particle or does it behave as a wave? We see that there are interference patterns where light obviously behaves like a wave. I mean, if it was just a particle, then the particle would just come straight out and come straight here, and it would be blocked by these barriers. But because it is a wave, it diffracts and it interferes. Now, all this pattern is obviously a wave pattern. But if it is acting like a hammer, and if it is not following the wave theory predictions, it could also be a particle. Well, as stated by quantum mechanics, light is both. It is a particle and it is a wave at the same time. Now that we've established this, there are a few essentials. The threshold frequency is the minimum amount of frequency required to carry forward photoelectric emissions. The work function is h into f naught, which is the threshold frequency. This is the amount of energy required to strike out an electron. Any energy lower than that will not produce any photoelectric emission. So we can hence deduce that the maximum kinetic energy of photoelectric emissions is hf, which is the actual frequency, minus hf naught, which is the work function, which is also the minimum amount of energy required to strike out an electron from the metal. Thanks and regards to photoelectric emissions simplified video. I may have made mistakes while speaking. I may have goofed up, and my accent may be irritating to some, but we covered a lot of things, including the wave particle duality of light, the fact that there are some properties of light that make it sound like a wave and some that make it sound like a particle. We saw how photoelectric emissions was uh, why it was so important to quantum mechanics, because it showed this dual nature of light, it being a particle and a wave at the same time. We also learned about the threshold frequency, which is the minimum amount of frequency required for photoelectric emissions to take place. We learned about the work functions and the formula for maximum kinetic energy. We learned about how Einstein changed history. Subscribe if you want more of this, so I know whether I'm actually making sense or no. Thanks. Bye.